In this section, we're going to learn how to graph in a new coordinate system. So we're very used to the rectangular coordinate system of graphing points by using the x and y values of those points. But we're just going to learn a new way in this particular section. So on the left here, we have our familiar rectangular coordinates, also known as Cartesian coordinates. So the x, of course, tells me how far left or right to go from the origin, and the y tells me how far up or down to go from the origin. So another way of doing it would be to say, first tell me how far away my point is from the origin. All right, and so we'll call that r, the distance from the point to the origin. And then if in addition to that you just tell me what kind of angle the line segment from the origin to our point makes with the x-axis, then that would be enough to locate any point in the plane. So instead of x comma y, we look at r, the distance from the origin to the point, and theta, the angle measured, remember the phrase in standard position, but that just means from the x-axis. Now r, we got to be a little bit careful. It's not technically the distance, because r, we're going to see, is allowed to be negative. So really, it's this absolute value of r that is the distance from the origin to our point. So let's just do an example where we kind of get used to this coordinate system and how to graph on it. Because it's based upon how far you are from the origin and the angle you make, rather than having a rectangular grid that we're used to when we look at graphs, we're going to have this, what we call a polar grid. So first of all, on our polar grid, let's notice that we've got some of the familiar angle designations, but there's also a few more. So here's 0 and 2 pi. Of course, up here is pi over 2. And so halfway between 0 and pi over 2 would, of course, be our pi over 4. But if this was just looking at the special angles, for example, on a circle that we memorized earlier in the quarter, we would really only want one other line below pi over 4 and one other line above it. So so this here is my pi over 6, and this here is my pi over 3. And you can see that this angle to this line here seems to be about half of pi over 6, and that's exactly what it is. It's pi over 12. And then this one over here, well, if this is pi over 12, this is 2 pi over 12, 3 pi over 12, 4 pi over 12, and this is 5 pi over 12. So just note that when you look at this grid here, we also are keeping track of, we're really having multiples of pi over 12 as we go around. All right, so as I graph these, first of all, we have 2 pi over 3, right? So 2 is my r, pi over 3 is my theta. So I start by saying, all right, I'm going to go out 2 from the origin. So that takes me out here. Here's, you can see a circle of radius 2. And then I'm going to go to the angle pi over 3. So staying along this radius of 2 line, I go to pi over 3, and so that puts that point right there. All right, grabbing a different color here. Now let's look at what would it mean to take 2 negative pi over 3. Well, I'm still going to go out 2 from the origin, but then I would go down to negative pi over 3, and so here's negative pi over 3 here. So go out to 2, sweep down to negative, an angle of negative pi over 3, and that puts me there. So we can have negative angles just like we've been working with all quarter. All right, now if I want 3 pi over 4, we'll use green for that one. So 3, I go out 3 to the circle of radius 3, and then I go all the way around to 3 pi over 4, which is right there. Okay, and then lastly, The last one's kind of the tricky one. So they give us a negative r value, right? So our r is -1. So here's what this means. Normally, if I went out 1 and then I went to 3 pi over 4, that would put me right here, right at 3 pi over 4. But -1 just means you go in the opposite direction. So I go 180 degrees back the other way. Okay? So you still think of it as I'm going to go to the angle they're telling me, but then I'm going to go the distance of 1 back in the opposite direction from the origin. All right, so that's what it means to have a negative r value. So now that we've graphed points in polar coordinates, let's talk about what it would mean to graph the curve from an equation in polar coordinates. So let's start just real simple here. So we have r is equal to 2. But, you know, r is supposed to be telling us about the distance of our points from the origin. So really this should mean that the equation r equals 2 gives me all points, a distance of 2 from the origin. Well, if we think about what is the shape that's formed when you get all points that are equidistant from the origin, you're going to get a circle, right? That's what you're always going to get. So I can sketch that pretty easily. Or not so easily on the computer here. We can use our imagination and pretend this is a nice circle. But our equation r equals 2 just gives us a circle. Now I want to show how that works on a calculator. So first of all, what we're going to do is we're going to go to mode. And in mode, there's a couple of things we want to do. First of all, we want to be in radian mode for graphs that we're going to be creating when we work in polar coordinates. So I'll put it in radian mode. But then you go down to this set of options: function, parametric, polar. We want polar. So we hit enter on polar, and then we go quit. And then, just like if we were in rectangular coordinates, we would go to y equals. I'll click on my y equals menu, but now it says r equals. So I can just put 2 in there. All right. And if I hit graph, okay, I get my graph, and of course it doesn't look like a circle, but remember that our window isn't all squared up. You can see the distances between tick marks on the x is different than for the y. And then you can also go to window. You can tell it what angles you want it to graph at, and so I'm going from theta equals 0 to 2 pi, which will be sufficient to graph my entire circle. And then of course you can adjust your x and y values as well. All right. Now, so we have the equation r equals 2 gives us a circle. Let's take a look at a more complicated equation in polar coordinates. All right, so that's going to be here in example 3. So it says we're going to look at r equals the secant of theta times the tangent of theta. Okay, let's see what that looks like. So, so over here, I go back to my y equals menu. I'll clear out the 2 that I had before. And of course, I don't have a secant button in my calculator, so I'll say 1 divided by the cosine of theta. And then I'll multiply that by the tangent of theta. And I'll hit graph and see what happens. So I get this graph here, and it certainly looks like a pretty familiar graph from rectangular coordinates, right? It looks just like a parabola. Okay, so let's see if we can convince ourselves that this in fact is a parabola. So I have r is equal to the secant of theta times the tangent of theta. Now let's think about how rectangular coordinates and polar coordinates relate to each other. If I superimpose the two pictures from our second slide together so that rectangular coordinates and polar coordinates variables are showing on the same picture, it becomes clear that really trigonometry is the key to understanding the relationship between rectangular and polar coordinates, right? So, because of the fact that I know that the sine of theta is equal to the y value divided by r, that tells me that y is equal to r sine theta. And similarly, since the cosine of theta is x over r, that tells me that x is r cosine theta. And then, of course, I know, because I have a right triangle here, that r squared equals x squared plus y squared, and finally that the tangent of theta is equal to y over x. All right, so over here we have, I think, quite a bit to work with. So first of all, everything's in terms of sines, cosines, or tangents. So this secant I'm not really thrilled about working with. So let's just go ahead and rewrite that as 1 over the cosine of theta times the tangent of theta. Okay. So I've got that. And then I know that the tangent of theta is y over x. So maybe let's start with that. So r equals 1 over cosine of theta times y over x. Now I also see right here that x is equal to r cosine theta. And I could make r cosine theta appear if I just multiply both sides of this equation by the cosine of theta. And on the right side, my cosines cancel. Okay, and so what I'm left with here, I've run out of room, but I'm left with, instead of r cosine of theta, I have x, according to this formula, is equal to y over x. And then if I multiply both sides by x, I get x squared equals y. And so we said at the outset that this, that this graph over here on our calculator certainly looks a lot like a parabola. And in fact, that's exactly what we get. We get that this equation is equivalent to y equals x squared. All right, just to make sure I'm clear here on this, since my spacing is really off, I'm saying this is my x value. So that x right there, that's replacing r cosine of theta, that's the x on the left side. So with the equations that we learned on the previous page, we can now convert points back and forth between rectangular coordinates and polar coordinates. So in this example, we've been asked to convert all these points in polar coordinates to rectangular coordinates. So I'm going to pick the two formulas from the previous page that already have x and y isolated. And these are going to be the way that I will make my conversions. So over here, I know my x is equal to 2 times the cosine of 5 pi over 6, which is 2 times, well, the cosine of 5 pi over 6 would be negative root 3 over 2, which is negative the square root of 3. And then my y value would be 2 times the sine of my angle, but the sine of 5 pi over 6 is positive 1/2, so that gives me 1. And so this point 2 comma 5 pi over 6 in polar coordinates is the same as the point negative root 3 positive 1, positive 1 in rectangular coordinates. And if you think about, on a circle, 5 pi over 6 we know is over here, right? That's over here. So this point should have a negative x value and a positive y value. So that lines up with the picture we know we should be getting from the polar coordinates. All right, so then this one here, x is equal to negative root 2 times the cosine of negative 5 pi over 4. Let's use a little symmetry here to simplify this. Remember that negative 5 pi over 4, if you take the cosine of it, that's the same as taking the cosine of positive 5 pi over 4. Right? Because the cosine is even. So the cosine of a negative is the same as the cosine of the positive value. And then 5 pi over 4, right? That is in quadrant 3. So the cosine is going to be negative there. So it'll be negative root 2 times, and when we have multiples of pi over 4, odd multiples of pi over 4, I should say, that's going to give me root 2 over 2. So negative root 2 times negative root 2 is, of course, positive 2 over 2, which gives me 1. And then y is equal to negative root 2 sine of negative 5 pi over 4. But that's going to be times, remember the sine of a negative is going to be the negative of the sine of the positive value, using that symmetry. So it's a negative times a negative is positive, so we'll have root 2 times, and the sine you can see at this location is also negative, just like the cosine. And I'm just about out of room here, but what we get is that the y value is negative 1. So what we end up with here is the point 1, negative 1. Now, before I got to be a little bit careful here. Remember, I was graphing 5 pi over 4, right? Not negative 5 pi over 4. So let's just be really clear about this, because you might look and say, wait, the x value is negative up here. But remember, our original angle was negative 5 pi over 4, and so I went this way, 5 pi over 4, which would put me there. Okay, but then since the r was negative, that would put me across the circle. So really, here's the point we're talking about over here. And you can see that that point has a positive x and a negative y. All right, and then lastly here, x equals, and this is going to be 4 root 3 cosine negative pi over 6. And the cosine of negative 5 pi over 6 is the same as the cosine of pi over 6, which we know is the square root of 3 over 2. So x equals 4 root 3 times square root of 3 over 2. And so we get a little cancellation here with the 2 and with the 4. And then root 3 times root 3 is 3. So 2 times 3 is 6. And then we do the same with our y value. Y equals 4 root 3, the sine of negative pi over 6. But that will be 4 root 3. The sine of negative pi over 6 is negative 1/2. And so that's going to be negative 2 root 3 after that cancellation there. So my point here is 6 negative 2 square root of 3. All right, so let's do the opposite. Let's go from rectangular coordinates to polar coordinates. Okay, so In this case, what we're going to be using is the other two formulas we didn't use in the last one. The fact that r squared is equal to x squared plus y squared, and the fact that the tangent of theta is equal to y over x. All right, so here, let's start with r. That seems easy. R squared is equal to negative 2 squared plus 0 squared. So r squared equals 4. And so r is equal to 2. And I'm just following the convention that it's asking me to make sure my r is greater than or equal to 0. So while it's certainly okay for me to have negative r's, they're telling me to convert it in such a way that we use a positive r value. So that's why I keep the positive there. All right, now for theta, right, the tangent of theta is y over x. So 0 over negative 2. All right, now we got to be a little bit cautious here. Don't be too quick to simplify, because on the unit circle, or on any circle for that matter, if you say, when does the tangent of theta equal 0, I think the most natural answer people give is at 0. All right, but of course it also happens over here at pi as well. And you'll realize which one you want if you keep both of these values. So yes, the tangent 0, but the tangent is 0 at, or the tangent is 0 in such a way where the sine is equal to 0 and the cosine is negative. Okay, so this is definitely the one that I want. So instead of saying theta equals 0, I'm going to say theta equals pi, because that's the spot on the unit circle where the y value is 0 while the x value is negative. So my point here is 2 pi. All right, so now let's look at b. All right, again, let's start with r. So r squared is equal to the x value squared plus the y value squared. So of course the square of negative root 3 is just 3. Square of negative 1 is 1. So hey, we have the same r value we did last time. R is equal to 2. But now the tangent of theta is going to equal negative 1 over negative square root of 3. And again, don't be too quick to simplify and get rid of these negatives. Let's just try to identify if these are special values on the unit circle, and they are. Anytime I have 1 and root 3 with a tangent, we should be thinking, okay, let's divide the top and the bottom by 2. And then I ask myself, okay, where is the sine, negative 1/2, and the cosine, negative root 3 over 2 on the circle? All right, well, they're both negative in quadrant 3, and that's going to happen right about here, right, where the cosine's larger and the sine is a smaller value. So that tells me that theta is 7 pi over 6. So my point here is 2, 7 pi over 6, written in polar coordinates. And then lastly, r squared is 1 squared plus 1 squared. R squared equals 2, so that means r is equal to the square root of 2. And then I have the tangent of theta is equal to 1 over 1. Okay, so when is the tangent of theta equal to 1? Or in other words, when is the sine and the cosine both the same? Well, we know that's happening at pi over 4, and it also does happen at 5 pi over 4, but it's pi over 4 when both are positive, right? And if you wanted to, you could say, okay, let's turn the top and bottom into root 2 over 2, right? And then that would also be a way of recognizing, oh yes, theta should be pi over 4. So the point is root 2 as r and pi over 4 as theta. All right, so now let's look at just a couple more equations like we did earlier. The one we did earlier was kind of a hard one, but I wanted to take an equation that was kind of an interesting one and convert it into rectangular coordinates just to kind of show how those formulas can work. But here we're going to go from rectangular to polar coordinates. And so we want to convert this equation here. And oftentimes you'll find that there are more than one way to do this. So some people might look at this and immediately realize that okay, I have an x squared and a y squared. And that might make them immediately think of the fact that r squared equals x squared plus y squared. And so if that's the realization you have, then what you should start by doing is to say, okay, 2 times x squared plus y squared, essentially factor that 2 out, minus 98 equals 0. And once you get x squared plus y squared, you can feel free to turn that into r squared. And so I can put 98 on the right side, divide by 2, r squared equals 49. And if r squared equals 49, it's safe to say that r equals 7. So what I have for myself here is a circle. Okay? And you can recognize that this thing can be rewritten as x squared plus y squared equals 49, which we would identify as a circle centered at the origin with radius 7. Okay? Now, let's say that you didn't immediately see the fact that you could make x squared plus y squared appear. If that's the case, you're not sunk. What you could do is say, all right, well, I know how to substitute out x and y. I can just use r cosine theta and r sine theta. So the other way of doing this, let me use a different color to make it a little easier to look at. The other way of doing this is to say, I'm going to take 2 times r cosine theta squared plus 2 times r sine theta squared minus 98 equals 0. And then as I square things here, I have 2r squared cosine squared theta plus 2r squared sine squared theta minus 98 equals 0. And then maybe at this point you'd realize, ooh, cosine squared plus sine squared, that's Pythagorean identity. Maybe I'll pull 2r squared out so I get that Pythagorean identity, and then that thing, of course, ends up equaling 1. All right, so even if you didn't recognize this right off the bat, you're not sunk. That's 1, so you have 2r squared minus 98 equals 0, which is the exact same thing that we came to at this point using this method here. Okay, now of course this is a little longer, so it's nice if you recognize that, but there's nothing wrong with doing it that way either. All right, now this one wants us to take another equation in rectangular coordinates and convert it to polar coordinates. And at first it might be tempting to try to somehow make r squared come about, but you know, we do need to remember r squared is x squared plus y squared. Okay, so it has nothing to do with x squared minus y squared. All right, so in this case, I think what's wise is to say, all right, let's just go ahead and use r cosine theta and r sine theta as x and y. So I'm going to write this as r cosine theta squared minus r sine theta squared. That's equal to 1. So r squared cosine squared theta minus r squared sine squared theta is equal to 1. Okay. Now, what I would like to be able to do in the end is I like to be able to say r is equal to some sort of a function of theta if possible. Because if you remember, when we looked at our calculator and looked at the y equals menu in polar mode, the places to put the formulas always looked like r equals. So that would be nice. And so I'd like to get r by itself, isolate it if I can. And so I've got r squared in both terms, so that means I can factor an r squared out of each term and be left with this. Now, always be on the lookout for ways that we can simplify. So this should look very familiar, and hopefully if you stare at it for a few seconds, you realize that what you have is the double angle formula for cosine. So this can become much nicer. So I end up with r squared and then cosine of 2 theta equals 1. All right, so again, with this idea that it'd be nice to get the r kind of by itself, I could say, all right, r squared is equal to 1 over the cosine of 2 theta. And then that would have to mean that r squared is equal to, well, 1 over the cosine is the secant of 2 theta. Okay. And this one, we will go ahead and leave this as is. Okay, we'll leave this as is. You can leave it as r squared is equal to the secant of 2 theta. So rather than turning it into r is equal to plus or minus. Okay, and then lastly, in example 8, it wants us to convert this into rectangular coordinates, so kind of something similar to what we were just looking at. And so we kind of have to do the reverse of the strategy we did before, right? So what I would like to be able to do is to find places where r cosine of theta shows up or where r sine of theta shows up. Okay? But notice it doesn't say anything about the cosine or the sine of 2 theta. But luckily, sine of 2 theta, we know that's our double angle formula, which says that's equal to 2 times the sine of theta times the cosine of theta. It's supposed to be a c there. Okay? But of course, we need r cosine theta and r sine theta. Okay, so let me do this. Let's take this formula here. I'm going to leave a little bit of space. All right. One of the things that's, I think, a virtue in mathematics is to use kind of wishful thinking, which says, you know what, I would really like it if an r showed up in front of my sine theta. That would really help me out. Okay, well, if that would really help me out, let's just do it. Let's multiply by r in front of the sine theta. Okay, but of course, if I do that to one side of my equation, I'm forced to do it to the other side as well. But as long as I do that, that's legal. And then, hey, I would really like it if there was an r in front of my cosine, because then that could be equal to x. And so that's fine as long as I do that on this side as well. And so overall, what I get here is that on the left, now I have r to the 4th. Okay, but over here I have 2 times, right, r sine theta, but r sine theta is y. And then r cosine theta, but that's x. And then over here, hopefully we recognize that what we've got going there is something with our formula r squared equals x squared plus y squared. So I'm going to rewrite r to the fourth as r squared squared. And so then my r squared can be replaced with x squared plus y squared. And try as I might, there's no way I'm going to be able to isolate y here. So this is a perfectly acceptable way to go ahead and write the answer. And graphs of this can be sketched. Your graphing calculators, again, not going to do that for you, but you can look at the graphs of things like this. So when you can't isolate y, you say, oh, that's too bad, but it doesn't mean it's not a valid graph to be able to look at.